Hi, this is John Whitaker for the graduate level probability class, and this is our 20th video lecture. And today we want to do more work working with conditional expectation. And so we had just gotten a fact having to do with finding the expected value of a random variable by taking the expected value of the conditional expectation. I'm going to remind you of that fact, and then we're going to do another example. Okay, so here's what we had. So as a fact, the expected value of a random variable x is equal to the expected value of the expected value of x given y equal to y. Okay. So let us use that in the following example. So suppose that the expected number of accidents per week at an industrial plant is 4. Suppose also that the number of workers injured in each accident are independent random variables so for each accident, they're independent random variables, the number got injured. Of the with common name two. Also assume that the number of workers injured in each accident is independent from the number of accidents. That will occur. Okay. What is the expected value? I'll say it this way. What is the expected number of injuries in a week? That's the question. Okay. So what's involved here is the number of injuries that you have in a week. And of course, that's kind of dependent on the number of accidents that you have and the number of injuries per accident. So what we're going to do for the solution is define the variables that we're have involved. So solution. So we're going to let n denote the number of accidents. And x sub I denote the number of injuries in the accident. The numbers injured. And here I can run from, well, it could be none. 1, 2, forever. Okay. Well, I think for I, you should start with 1, 2, 3. Okay. Now, here, then the total number of injuries is, well, it's x equal to the sum as I runs from 1 to n, big N, of x sub I. So the expected value of x is equal to the expected value of x given n equal to n. So it depends on the number of accidents we have. Okay. So we're conditioning on the number of accidents that occur. And so let's look at that. So note the conditional expectation of the number of total accidents, or injuries, I should say, given n equals little n. That's the same thing as the expected value of the sum as I runs from 1 to n of x sub I given n equal to n. And that's equal to okay, so here we could think of this as a bunch of random variables we're adding up. So what we have is this would be equal to the sum as, let's say, x sub 1, sum over x sub 2, sum over x sub 3, sum x sub big N, okay, of x sub 1 plus x sub 2 plus all the way up to x sub big N. So these are discrete random variables. I'm going to use the conditional PMF of x sub 1, x sub 2, all the way up to x sub n, given n, and this will be x sub 1, x sub 2, all the way up to x sub n, given n equal to, well, here it just be little n. All right, so that's what we have. Now, we can rewrite that second part. So the first part, the sum, we'll leave as is. This will be x sub 1 plus x sub 2 plus all the way up to x sub n, big N, And here, we rewrite this as the joint PDF between x of 1 up to x of n, big N here, and big N, x of 1, so here I'll say x, well, just x of 1, comma x of 2, all the way up to x of n, and then comma n, all over f, so big N equals to little n. Now, you can rewrite these in terms of probabilities, so that joint PMF, okay, in terms of probability. So this is the sum over x of 1, sum over x of 2, all the way up to the sum over x of n, the output values, of the x of 1 plus x of 2 plus all the way up to x of n. And here, what this is going to be, because of independence, this is f sub x of 1, the joint PMF between x of 1, x of 2, all the way up to x of n. Well, I shouldn't say it. Let's write it in terms of probability, as I said I was going to do. This is times the probability that x of 1 equals to little x of 1, x of 2 equals to little x of 2, all the way up to x of n equals to little x of n, and then finally, n equals to little n, over the probability, that's probability, that big N equals to little n. And now due to independence here, we can split this up. This probability in terms of a multiplication probabilities. Not only that, but because we know we're having a situation where n has to be equal to n, little n, then that means the random variables involved go up to x of big N will just be x of little n. Because the other situation would just be 0. Probability would be 0. So that's equal to the sum x of 1 up to the sum of x of n of x of 1 plus x of 2 plus all the way up to x of n, little n this time. And here just the probability that x of 1 equals to little x of 1, comma, all the way up to big X of little n equal to x of n, times the probability that big N equals to little n, all over the probability that big N equals to little n. These two things will cancel. This is the sum, x of 1. All the way up to the sum over x of n. X of 1 plus x of 2 plus x of n times the probability that x of 1 equals to x of 1 times probability, well, they're independent of each other, so if you wanted, you could say times probability that x of 2 equals to x of 2, all the way up to the probability that x of n equals to little x of n. If you multiply this out, and if you multiply all this out, well, what you'll find is that for a lot of these items, they do not depend on the index. And so what you end up getting here is, if you will, a sum of x of 1, well, I'll still write it all out, up to x of n, of x of 1 times all this. Plus, you keep on having these n number of sums, because you're distributing here and then just taking the sum of each one of these guys once you distribute all this. So the last one's x sub n has probability of x sub 1 equals to x sub 1 times probability that x sub 2 equals to little x sub 2, and then times the probability that x sub n equals to little x sub n. Put that it's in there. I think you can see it. We know it should be. And now, when you do this first sum, that's nothing more than the expected value of x sub 1. And the next sum is going to be the expected value of x sub 2. And then that's the last one is the expected value of x sub n. Okay? But they're identically distributed. They all are the same. And so this is the same thing as n times the expected value of x sub 1. Okay. So what we've just shown is that the conditional expectation of x given n, okay, is, well, let's just put it like this, is the random variable n times the expected value of x sub 1. So it's whatever n is. So, the expected value, the conditional expected value of x given n equals to little n is nothing more than the expected value of this guy is n times the expected value of x sub 1. The expected value of x sub 1 is a constant. We pull that out. So that's equal to the expected value of x sub 1 times the expected value of n. But these two expected values were given to us in a problem. So I think the expected value of x sub 1 was 2. So the number of accidents, I think, number of injuries per accident was 2. And the expected value of n was 4, so we end up getting 8. And that's the solution for this problem. This type of random variable that we just looked at is this x in this problem is a noteworthy random variable. It's something that's studied. And so we're going to give it a special definition. It's going to be called a compound random variable. And we'll come back to that. So as a definition, the random variable x equal to the sum as I run from 1 to n of x sub I, which is the sum of independent sum of a random number, let's say, n, of independent and identically distributed random variables that are also independent of n. Is called a compound random variable. Okay, we'll state facts about compound random variables, and part of which we just proved it. So, as a fact, if X is a compound random variable, with X equal to the sum as I runs from 1 to n of X sub I, then the expected value of X is equal to the expected value of X sub 1 times the expected value of n. And as a comment, we proved this fact in our solution to the previous problem, when the Xi's are discrete random variables. That's a fact. Okay, the remainder of the lecture so for the remainder of the lecture, we're going to use conditioning to find the expected value and the variance for a geometric random variable. Okay, and so we had found and listed the expected value of a geometric random variable. So we found that in an earlier lecture, and we used kind of formally the power rule to do this, and then we just stayed with the variance was, but now we can actually prove the variance and the expected value in a non-formal way. So, so let me write that down. Excuse me. We will next compute the value, the expected value of a geometric random variable using conditional expectations. Okay, so what was a geometric random variable? So here was the definition. We call it an example because we're using this to illustrate how we can use conditional expectations to compute things. So let a Bernoulli random experiment be performed independent times, independently, until, so the geometric was having to do with the first success. The first success occurs. Okay. Where was the probability of success? Well, that's going to be P. Where the probability of success equals to little p. Okay. Let n count the number of times the experiment was performed. Okay, so what we're trying to do is compute. So n is geometric, and we're trying to compute the expected value of n. And we will later compute the expected value, the variance of n, in just a few minutes. So we're going to do this through conditional expectations. So here's what we're going to do. We're going to condition based on whether the first time we did the experiment was a success or not. So we're going to define, or let y be equal to 1 if the first trial is a success. And 0 if the first trial is a failure. Okay, so the expected value of n is the same thing as the expected value, the conditional expected value of n given y equal to y. Now, this is an expected value of a function of y. So its answer is the sum as y runs from its values, which are either 0 or 1, of this random variable, so that's the expected value of n given y equal to y, times f sub y of little y. So that's the expected value of n given y equal to 0 times the probability that y is equal to 0 plus, this is what that sum is. The expected value of n given y equal to 1 times f sub y of 1. Okay. Now here I'm going to say things. But first I can fill in for what this is. So this expected value of n given y equal to 0. What's the probability that y is equal to 0? Well, that means that the first success was a failure. Chance of that is 1 minus p. Plus, this is the conditional expected value of n given y equal to 1. What's the chance that the first trial was a success? Well, that's just p. Now, I'm going to state these things, but I'm going to prove them. But here, this part, the expected value of n given y equals to 1, well, you're saying that the first trial was a success. So you ask how many trials did it take. Well, if you know the first trial was a success, on average, the number of trials it's going to take is 1, because the first trial was a success. The number of trials to get the first success would be 1. This one, however, ends up being, and you can kind of reason through it. So I'm going to prove this. Note, the expected value of n sub y equal to 1 equals to 1, that part. And the expected value, the conditional expected value of n given y equals 0, well, that's going to be equal to, well, knowing that the first time you did it, you didn't get a success, that would be the same thing as the expected value of n, when you didn't know whether you were going to get a success on the first try or not, plus 1. It should be 1 more, because you know the first time you did it here, you got 0. So we'll argue why those two are the right answers. Okay, so 1. So this one's the easy one. So where the conditional expectation of n given y equals 1. Okay, this would be the sum over all the n values, so n running from 1 to infinity, of n times, well, we have f sub n given y, here it will be n given y equal to 1, which is equal to the sum as n runs from 1 to infinity of n times f of n equal to little n and y equal to 1 over probability that y equals to 1. Now, if you want, this is the probability that n is equal to n and y is equal to 1. Well, that means that that's the same thing as the probability of y equaling 1. So this is the same thing. It's the sum as n runs from 1 to infinity, and n has to be equal to 1. So really, it's just one item in your sum. It's just 1 times f sub y of 1 over f sub y of 1. And so they're the same, so you just get 1. So again, it boils down to this. What's the probability that big N is equal to N and Y is equal to 1? That's the same thing that the probability Y is equal to 1. And N has to be 1. And N equals 1. Okay, so that's that part. The other part here is a little bit more complicated. Now, the conditional expectation of n given y equal to 0, that's the sum as n runs from 1 to infinity, of n times f of n equaling to n, y equaling to 0, over f sub y of 0. All right, f sub y of 0 is something I can get. So this is equal to the chance that y was equal to 0, the chance that y is equal to 0 is chance of a failure, that's 1 minus p. So it's 1 over 1 minus p. That doesn't depend on n, so I'll take it out of the sum. Sum as n runs from 1 to infinity. N times f sub n equal to n, and y equals to 0. Now, here's what I'm thinking. So, we could have 1 times f sub big N equal to 1, y equals 0. Well, that probability that f sub n equal to 1, y equals 0, it's got to be 0. Because the chance that it only took one trial to get the first success when you knew the first success is failure is 0. Okay? Chance of that happening is 0. So this is 1 over 1 minus p times the sum as n runs from 2 to infinity of n times f sub n equal to n, y equal to 0. So this probability n is equal to some n where n runs from 2 to infinity, and y is 0. Well, if you know n running from 2 and bigger, the number of trials needed is 2 or more, you already know that y is equal to 0. So this probability just reduces to the probability that f sub n is equal to n. So this is equal to 1 over 1 minus p. Sum, as n runs from 2 to infinity, of n times f sub n of n. That's the way I can write it. Okay. Now that's the probability that n is equal to n. So 1 minus p sum n runs from 2 to infinity n times probability. Big N equals little n. Okay, just to make things look a little bit clearer, in terms of the formatting here, let's let J equal to n minus 1. Okay, so still dealing with this quantity, we have 1 over 1 minus p sum. So J runs from 1 left, so J would run from 1 to infinity. Wherever there's an n, I write down J plus 1 times the probability that n is equal to, okay, this would be J plus 1. What we're going to do is we're actually going to figure out this probability. So what was n? N was the chance that n is the random variable that tells us how many trials we have to do. So the probability n is equal to J plus 1, we can compute. Because we know what that should be based on the PMF of geometry. And being able to reason through that. So that's equal to 1 over 1 minus p. Then we have the sum, J runs from 1 to infinity, of J plus 1 times, well, that's the chance of success of the last trial. So we're saying it took J plus 1 trials to get our first success. That means the J plus 1 trial was a success. What's the chance of that happening? P. What's the chance that the other guys were failures? 1 minus P can be raised to the J. Okay. You pull out one of the 1 minus p's. Sum as J runs from 1 to infinity. This is J plus 1 p times 1 minus p to the J minus 1. Okay. If you want, you can rewrite this in terms of n. So we're going to let n be equal to J. So this part is equal, that's 1, sum, it's n running from 1 to infinity. This will be n plus 1, p, times 1 minus p to the n minus 1. So I didn't do anything except just change the letters to get back in terms of the variable n. Okay. Now, that's equal to, the sum is n runs from 1 to infinity of n times p times 1 minus p to the n minus 1 plus the sum is n runs from 1 to infinity of p times 1 minus p to the n minus 1. Okay. This is the sum of the PMF for a geometric random variable, and so we know it's equal to 1. You can get that by the binomial theorem. I'm sorry. You can get that by a geometric series. I said the wrong thing. So that part's going to be excuse me. And this part right here is nothing more than the expected value of the geometric random variable n. So that's what I'm going to write next. So that's equal to the expected value of n plus 1. So that proves what we had already reasoned through. Okay. So, the expected value of n Remember, this was our question, which was equal to the expected value of n given y, which we found to be, forgive me, we have found that already to be equal to the expected value of n given y equal to 0 times 1 minus p plus expected value of n given y equal to 1 times p. But we just found these values for y. Let me write this down. So this takes some algebra. So the expected value of n, right here, is equal to, well, this part we just found over on the left-hand side of the board. It was the expected value of n plus 1 times 1 minus p. Here this was 1. Multiply this out, we get the expected value of n is equal to the expected value of n minus the expected value of n times p plus 1 minus p plus p, so that's just 1. And that's equal to, I should say, so, all right, look, I pulled it back. Let's go back. Here's what I'm going to do. What am I trying to solve for? I'm trying to solve for the expected value of n. So I'm going to get all the expected value of n's. I mean, this is solving a linear equation, if you will. I'm going to bring the expected value of n's over here. So what I'm going to get, when I move this over here is 0. When I move this over here, I'm going to get expected value of n times p equal to 1. That's what I'm going to write. What we get is expected value of n times p is equal to 1. And so, the expected value of n, that's a geometric random variable, is equal to 1 over p. And that is indeed what the expected value of a geometric random variable is. It's 1 over the probability of success. That's great. Okay. We can use conditional expected values to compute variances. And this is the last thing we'll do. Okay. So as an example, and this has to do with a geometric random variable. Okay. So suppose independent trials each resulting in a success probability P are performed in series. Let N be the number of trials until the first success So N is the trial for which you had the first success. Find the variance of N. Okay. Well, so for our solution, we'll do the same thing that we did before. We're going to do a conditional expectation, where we're going to conditional on random variable y. So again, we're going to let y y is going to be the same thing. 1 if the first trial is a success. And 0 if the first trial is a failure. Okay. Now, what are we looking for? Well, I guess I should say this. Note, the variance of N, that's what we're looking for. That's the expected value of N squared by formula minus the expected value of N to B squared, which we already have. We proved that just a few minutes ago. It's 1 of B squared. So that's what we're working with. Now, the expected value of N squared will be equal to the expected value of N squared given y equal to y. And if you perform the similar work we did before, so first of all, we're having a random variable called N squared, so it's still going to work with the formula we proved. But you could, in the case of discrete random variable, check that out if you want to, using this definition here to get that side. That's what we did when we proved the expected value of x was equal to the expected value of conditional expected value of x given y equal to y. So do it again for N squared. What's this going to be equal to? Okay. This is going to be equal to the expected value of N squared given y equal to 0 times the probability of y equals to 0, just like what we did before, plus the expected value of N squared given y equal to 1 times the probability of y equals to 1. And now, instead of doing all that work again here, I'm just going to say, well, the expected value of N squared given y equal to 1. Okay. That's telling us that the first trial was a success. What should be the expected value of N squared, the number of trials needed? Well, that should just be 1. Okay? And so I'll say as if the first, so here I'm writing that out, trial was a success, okay? The expected value of N squared is 1. Okay? That's what I just said. For the other part, we got to do some more. What other part? The expected value of n squared given y equals 0. That's what we're going to work on. Okay. Now, the expected value of n squared given y equals to 0 equals, well, that would be the sum, as n runs from 1 to infinity, of n squared times the probability, I'll write f sub n of y n 0, which equals to the sum as n runs from 1 to infinity of n squared. Here this will be the probability that n equals to n, y equals to 0, over the probability y equals to 0. As we're talking about discrete random variables. This is the conditional PMF. I just rewrote it in terms of what it's equal to. Which is equal to, well, the probability y is equal to 0, we already did that. That's, well, 1 minus p. I can pull that out. This is the sum as n, wait, where's the 1 minus p? 1 over 1 minus p. Sum as n runs from 1 to infinity of n squared times the probability that n is equal to n and y is equal to 0. Well, if y was equal to 0, the first trial would be a failure. So when you let n be equal to 1, the probability, the number of trials you had to do it would be 1, and the first would be a failure. That'd be 0. So the first term of this sum is 0, so no use having that. But will is 1 over 1 minus p times the sum as n runs from 2 to infinity, just like what we did before, of n squared times the probability that n is equal to n and y is equal to 0. But look, the event that n is equal to little n and y equals to 0, when you know n is going to run from 2 to infinity, it's just the same thing as probability n equal to n. So this is 1 over 1 minus p times the sum as n runs from 2 to infinity of n squared times the probability n is equal to little n. Okay. Let us again do the same thing we did before by introducing a new variable. So, but first, let's do one more thing. This is equal to 1 over 1 minus p, sum as n runs from 2 to infinity, n squared. I can calculate that probability. That's p, probability of success, times 1 minus p to the n minus 1. Good. Again, we're going to let a dummy variable j be equal to n minus 1, just as we did before. Same work. Okay, so that's equal to 1 over 1 minus p, sum as j would run from 1 to infinity. It would be j, so n, j is equal to n minus 1, so n is equal to j plus 1, so we have j plus 1 to b squared. P times 1 minus p to the j. We pull out a 1 minus p. Sum j equal to 1 infinity. J plus 1 squared p, 1 minus p to the j minus 1. Then, yeah, that's where we are. I'm going to let j be equal to n. Just so we get everything back into that original variable. This is 1. So we have the sum as n runs from 1 to infinity. N plus 1 to b squared, p times 1 minus p to the n minus 1. We can multiply that out. Or you could just say, well, that's nothing more than the expected value of the random variable n plus 1 to be squared. That's what that is. Okay, so that's equal to the expected value of n. Well, we could use that algebra trick again. So let's start off, let's go back to what we were finding. So this expected value of n squared is equal to the expected value of n plus 1 to b squared. That's what we found. Well, that part. And then that was times 1 minus p. Okay, so that was the expected value of n given y equals 0. Times 1 minus p. Plus, it was 1 times p, so just p. So, look, all this work was to find, remember what this was. This was the expected value of n given y equal to 0. Where was it involved? It was involved in calculating the expected value of n squared, because the expected value of n squared was the expected value, conditional expectation, of n given y equals 0 times 1 minus p, plus the expected value of n given y equals 1 times p. All right. So let's see. So expected value of n squared, I'm just going to use algebra. This is expected value of n squared plus 2n plus 1 times 1 minus p plus p. So the expected value of n squared is equal to the expected value of n squared plus 2 times the expected value of n plus the expected value of 1 is just 1 times 1 minus p plus p. So the expected value of n squared is equal to the expected value of n squared minus p times the expected value of n squared. We just found this to be 2 over p times 1, and then plus 2p over p plus 1 minus p, and then plus p. So here again we pull out, we subtract expected value from n, expected value of n squared from both sides. We get 0 from n. Then we add p times the expected value of n squared. So we have p times the expected value of n squared is equal to, let's see, what is this? This is 2 over p plus, let's see here. So here, this should be a minus, I think. I made a mistake, minus. So 2 over p. So that's a minus, right? Because this is 1 over p, 2 over p is what this is. And times 1 is 2 over p. Minus 2p over p. That's right. So the minus p here and the plus p makes 1. Here is a minus 2, so we end up getting a minus 1. That's a minus 1. So p times the expected value of n squared equals to 2 minus p over p. So that tells me that the expected value of n squared is equal to 2 minus p over p squared. All right, that's what we got by conditional expected values. So now we're ready to answer for the variance of n, the variance of a geometric random variable. So the variance of n, which we remember is the expected value of n squared minus the expected value of n to b squared, which is equal to, well, we just found this, that's 2 minus p over p squared. We found this earlier, 1 over p squared. So the 2 minus 1, that's just 1 minus p over p squared. And that is what the variance for a geometric random variable is equal to. 1 minus p over p squared. Thank you very much. That's enough for this video lecture.